All right, so let's dive into symmetry. You might be surprised just how deep this topic goes. I know as a philosopher, you're probably thinking about aesthetics and geometry.
Yeah.
But trust me, symmetry in modern physics is a whole other thing, like another dimension almost. We're talking about symmetries that are built into the actual laws of the universe, like in the fabric of reality.
It's pretty fascinating. It's not just about pretty patterns and balances, though. It's really about the deeper structure of the laws of physics. The underlying principles that govern how everything works, from tiny particles all the way up to the cosmos.
Yeah, and our deep dive today is based on excerpts from the Stanford Encyclopedia of Philosophy's entry on symmetry and symmetry breaking. So get ready, because we're going to be dealing with some pretty big questions here.
Oh,
Like,
yeah, yeah.
how did we get from the ancient Greeks thinking about symmetry to how we think about it now in modern physics?
Right.
What does it even mean for a law of physics to be symmetrical? Can something really come from nothing? Or is it all about asymmetry that leads to the existence of everything?
We're also going to be looking at some mind-bending connections. Like, think about your left and right hands. What does that have to do with space?
Yeah, what is that all about?
And can symmetries be broken? Like, how does that happen? And what does it mean for reality when these fundamental symmetries kind of shatter?
To understand all of this, we're going to need to look at some key concepts,
Yeah.
like symmetry principles, symmetry arguments, and of course, this idea of symmetry breaking. So buckle up.
Yeah, let's start by looking back, tracing how this concept has changed over time. So the word symmetry itself comes from the ancient Greek words sun, meaning with or together, and metron, meaning measure. And initially it was all about this idea of commensurability, concept you can find back in Euclid's Elements.
So they were already thinking about how things fit together back then, but in a measurable and balanced kind of way.
Yeah, exactly. But the concept developed and broadened to include this idea of a relationship of proportions, based on numbers, where you kind of harmonize all these different elements into a unified whole. And think about how important symmetry was to the ancient Greeks in their philosophy and in their natural philosophy. Harmony, beauty, unity, all of these things, they were seen as reflecting a deeper cosmic order.
Like Plato.
Yes.
He was obsessed with these perfect geometric solids, right? Assigning them to the basic elements, like earth, air, fire, and water, and even to the universe itself in his Aeneas.
Right. Now, those specific models may not have been totally accurate,
Right.
but they do show how powerful this belief was that symmetry held the key to understanding the natural world.
Yeah.
But, the modern scientific concept of symmetry, it took a bit of a different turn in the 17th century.
Okay.
Instead of focusing so much on proportions, there was this shift to this equality between opposing elements. Like, think about the left and right sides of a figure.
Okay, so more like a mirror image where you can swap the parts without changing the whole form.
Yeah, exactly.
Yeah.
And the big realization here is that these parts could be interchanged relative to the whole thing. And you combine that with the mathematical operations that were developing at the time, reflections, rotations, translations, and that led to what we call the crystallographic notion of symmetry. So here, symmetry is defined by invariance under these operations.
So like if you take a perfectly symmetrical snowflake
Right.
and rotate it 60 degrees, it looks exactly the same, right?
Exactly.
That's that invariance under rotation.
Yeah.
And if you flip it over like a mirror image, it's also invariant.
Exactly. And this crystallographic concept was further refined in the 19th century thanks to the development of group theory. And it provided this more robust mathematical framework to understand this.
Okay.
So now, symmetry is rigorously defined as invariance under a specific group of transformations.
Okay. Groups, transformations.
Yeah.
This is starting to sound a bit abstract for a simple concept like symmetry. Like, why does this actually matter for physics?
Well, because this shift to a group theoretic framework revolutionized how we could apply symmetry to the study of the universe. So suddenly we could talk about the symmetry of mathematical expressions and, crucially, about the equations that describe physical laws. We moved from the symmetry of objects to the symmetry of the laws that govern those objects.
Oh, I see. So it's not just about visual symmetry anymore. We're talking about something deeper, the structure of the laws themselves.
Exactly. And this leads us to two key distinctions when we talk about the historical role of symmetry in physics. One, implicit versus explicit uses of symmetry. And two, symmetry principles versus symmetry arguments.
Okay, so let's break those down. Implicit versus explicit. What's the difference?
So implicit uses of symmetry are kind of like baked into our understanding of the world, even if we don't explicitly call them symmetries. Like, think about the homogeneity of space, the idea that the laws of physics are the same everywhere. Ancient philosophers and early scientists, they relied on this assumption, even without the formal language of symmetry.
So they basically took it for granted that the universe plays by the same rules everywhere.
Pretty much, yeah. It was just an intuitive part of how they viewed the world. But then we have explicit uses of symmetry, where we're consciously applying the concept of invariance under transformations to physical laws and phenomena.
And that brings us to symmetry principles and symmetry arguments.
You got it. Symmetry principles, they involve like attributing specific symmetry properties to phenomena or to laws. So, for example, the Galilean principle of relativity. This states that the laws of physics are invariant under Galilean transformations. Like, think about those between reference frames that are moving at constant velocities relative to each other.
So, like, whether you're standing still or on a train that's moving smoothly, the laws of physics work the same way.
Exactly. Galileo famously used this principle to argue that you can't actually determine whether the Earth is moving or stationary just by watching how things behave on its surface.
Oh, that's a pretty elegant way to put it. I like that.
Mhm.
So then what about symmetry arguments? How do they differ from symmetry principles?
So symmetry arguments, they're all about deriving specific consequences, about particular physical situations based on their symmetry properties. And so they allow us to predict how a system will behave without needing to know every little detail about the underlying physics, just by analyzing its symmetries.
So it's kind of like a powerful tool. Symmetry can be a shortcut to understand how things work.
In a way, yes, it's like a powerful tool to analyze and predict things in physics. One famous example of that is Pierre Curie's work on symmetry breaking in the late 19th century. He argued that, for a phenomenon to occur in a medium, you have to actually break the original symmetry of that medium.
Oh, so to get something rather than nothing, you need a bit of asymmetry. That sounds kind of profound. Tell me more about Curie's work.
So Curie, his insight was that asymmetry is actually this driving force behind observable phenomena.
Oh, wow.
And he expressed this in what we now call Curie's principles. That is, the symmetry elements of the causes must be found in their effects, but the effects can be more symmetrical than the causes.
Wait, hold on. The effects can be more symmetrical. How did that work?
So imagine like a perfectly spherical, uniformly heated ball. It has a high degree of symmetry, right?
Yeah, it looks the same from every angle.
But if you were to cool one side of the ball, what you're doing is you're creating a temperature gradient, right?
Right.
You're breaking the spherical symmetry. So now the ball has like a preferred axis, the one along that temperature gradient.
Okay.
But even though we've broken that spherical symmetry, the ball still has cylindrical symmetry.
Okay.
So it's the same if you rotate it around that new axis.
Oh, so we've broken the symmetry, but not completely gotten rid of it. There's still some order left.
Exactly. And this is where Curie's principle comes in. The cooling process, that's the cause, it has less symmetry than the resulting state of the ball, which is the effect.
Right.
So the effects can actually exhibit emergent symmetries that weren't there in the causes.
That's a great example of Curie's principle.
Yeah.
It seems like this idea of symmetry breaking is really important in understanding the universe's complexity. But you mentioned that it also gets kind of controversial.
Yeah.
Tell me more about that.
Well, Curie's principle, especially how it applies to spontaneous symmetry breaking, has caused quite a bit of debate, about how it's justified, about its limits, and what it means for causality and our understanding of physical laws.
It sounds like we have a lot more to cover. We've gone from ancient Greek geometry to Curie's principle and this really interesting idea of symmetry breaking. But I have a feeling this is just the beginning of the story of symmetry in physics, right?
You're right, it doesn't end there. It actually gets even more interesting when we get to the 20th century in modern physics.
Okay, already let's hear it, the next chapter. What happened in the 20th century that changed how we think about symmetry?
Well, the 20th century brought a huge shift in how we view symmetry in physics, and a lot of that is because of Einstein. So before him, symmetry principles were seen as consequences of the laws of motion, not really fundamental in themselves.
So like it was a bonus, like a nice thing to have, but not the main show.
Exactly. But then Einstein kind of flipped this whole idea on its head.
Okay.
With his theory of special relativity, he postulated the universality of certain symmetries as like the starting point,
Oh, well.
It was like he said, these symmetries, they're fundamental, and the laws of physics, they have to respect them. Think about the homogeneity and isotropy of space, and the uniformity of time.
Okay.
These weren't just consequences anymore. They were the foundation that the laws of physics were built on.
Wow, that's a big change in perspective.
Yeah.
So Einstein kind of elevated these symmetries to the status of like almost foundational principles.
Yeah, exactly. And this approach has been so fruitful in 20th and 21st century physics. You see, the invariance of physical laws under certain transformations allows us to actually formulate these laws in a way that works regardless of the observer's reference frame.
So whether you're watching an experiment from a stationary lab or like a spaceship flying through space, the underlying laws are still consistent. That's pretty neat. I like that.
Elegance, that's a good way to put it.
Yeah.
It shows you the power and the beauty of these symmetry principles.
Right.
They give us a framework for understanding the universality and the objectivity of physical laws, even when we see observations that seem really different.
Right. Right. Okay, so what about Einstein's theory of general relativity? Didn't he kind of use a similar approach with symmetry there?
Yeah, absolutely. So, at the heart of general relativity is this principle of general covariance.
Okay.
This principle says that the laws of physics should be formulated in a way that doesn't depend on the specific coordinates we use to describe spacetime.
So no matter how you slice and dice it, the laws hold
You
true.
got it. But the role and the significance of general covariance in general relativity has been debated a lot, among physicists and philosophers. Some say it's a really powerful principle that restricts the possible forms of gravitational theories, while others say it's just a formality without much physical meaning.
Hmm. It sounds like we could do a whole other deep dive just on that debate.
Yeah.
But for now, I'm curious how these symmetry principles work in the quantum world. Is it all just as neat and tidy down there?
The quantum world, oh, it's anything but neat and tidy, but that's
Hmm.
what makes it so cool. And yeah, symmetry principles, they play an even bigger, more profound role in quantum mechanics.
Oh, really? How so?
Well, remember those groups of transformations we were talking about earlier?
Right.
Well, in quantum mechanics, those transformations are represented by operators that act on the state space of a system.
Okay.
These operators correspond to physical observables and their eigenvalues. Those are like the possible outcomes of measurements. They provide labels for classifying the states of the system.
Okay, I'm following so far. But how does this connect to the idea of symmetry?
So here's the key. If a system has a certain symmetry, the operators representing those symmetry transformations, they will commute with the Hamiltonian of the system. What that means is that those operators represent conserved quantities.
And served quantities, you mean like energy and momentum?
Exactly. So symmetry principles in quantum mechanics are directly connected to conservation laws.
Hmm.
This has huge implications for how we understand fundamental particles and their interactions.
Okay, so let me see if I've got this right. We've got symmetry principles that are like fundamental to physical laws, and those principles lead to conservation laws in quantum mechanics. So symmetry isn't just some mathematical curiosity, it's built into reality itself.
Yeah, that's a really nice way to put it. And the cool thing is we can classify and understand how particles behave based on their transformation properties under these symmetry operations.
So symmetry gives us this really powerful tool to organize the incredible diversity of particles in the quantum world.
Exactly. And it's not just about like spatial symmetries, like rotations and translations. Quantum mechanics introduces this whole new world of internal symmetries, things like isospin, which relates protons and neutrons as like different states of the same particle.
Isospin, that's a new one for me. Are you saying that protons and neutrons, these seemingly different particles, are like two sides of the same coin because of this internal symmetry?
Yeah. In a way, they transform into each other under the operations of this isospin symmetry group.
Wow.
And this idea extends to other particles, leading to the classification of particles into families based on their internal symmetry properties.
So symmetry provides this like hidden connection between particles, a deeper order beneath all the variety we see. It's like a secret language or a code that governs the relationships between these fundamental building blocks of matter.
That's a great way to think about it. And this is where things get even more interesting because not all symmetries are exact,
Right.
Some are broken. And this breaking of symmetry is what gives rise to the huge variety of phenomena that we see in the universe.
Symmetry breaking. We talked about this a little bit before with Curie's principle. I'm excited to dive deeper into this. What does it mean for a symmetry to be broken, and what does that mean for our understanding of physics?
Well, there are different types of symmetry breaking. You can have explicit symmetry breaking, where the laws of physics themselves aren't perfectly symmetrical. A classic example is the violation of parity or mirror symmetry in weak interactions. So that means that some physical processes actually happen differently if you view them in a mirror.
So nature has like a slight preference for one hand over the other. That's pretty wild and a little unsettling too, if you think about it.
It was a huge discovery that really challenged our ideas about the fundamental symmetries of the universe.
Hmm.
But there's another type of symmetry breaking. Spontaneous symmetry breaking. This is where the laws of physics are perfectly symmetrical, but the ground state, the lowest energy state of a system, it's not. This is where Curie's work on symmetry breaking comes back in.
So the laws themselves are symmetrical, but how those laws actually work out in the real world can lead to asymmetry.
Right.
It's like the universe has this potential for perfect symmetry, but something happens that pushes it into a less symmetrical state.
Exactly. It's like a perfectly symmetrical pencil balanced on its tip. The laws of physics are the same whether it falls to the left or to the right.
Right.
But once it falls, the symmetry is broken.
I see. So the pencil could fall either way, but it has to choose one, and that choice breaks the symmetry.
Yeah.
Even though the underlying laws for the pencil are symmetrical, the specific outcome isn't predetermined.
Yeah, that's a great analogy. And in the quantum world, spontaneous symmetry breaking is responsible for all kinds of amazing phenomena. From the existence of mass to the behavior of superconductors, even the large-scale structure of the universe.
Wow, so this concept has some pretty big implications. I'm starting to understand how symmetry and symmetry breaking aren't just some abstract mathematical ideas, but like fundamental principles shaping reality itself. They're like the architects of the universe working behind the scenes.
Yeah, that's a great way to put it. And maybe the most amazing example of spontaneous symmetry breaking is the Higgs mechanism.
A Higgs mechanism,
Yeah.
the one that gives particles mass. I've heard of it, but I have to admit it always sounded kind of magical to me. Like, how can something come from nothing?
It's not magic, but it's definitely mind-bending. The Higgs mechanism is a little bit like your pencil analogy, but instead of a pencil falling, we have a field that acquires a non-zero value in the vacuum.
A field acquiring a non-zero value in the vacuum. Okay, that's where I get lost. What does that even mean?
Think of it like this. Imagine this huge, perfectly flat plane. That's the vacuum, the state of lowest energy. Now imagine a ball rolling across this plane. It's free to move. It has no mass.
Okay, I'm picturing it, a massless particle just zipping through the vacuum.
Now imagine that the plane develops a bump, like a little hill. If the ball rolls over this bump, it's going to slow down, right?
Right.
It's like it acquired mass.
Okay, so the bump in the vacuum is giving the particle mass. But where does the bump come from?
That's where the Higgs field comes in. So the Higgs field is like this invisible plane that's everywhere in space. And when it gets a non-zero value in the vacuum, it creates these bumps that can interact with particles and give them mass.
Okay, so it's not that something's coming from nothing. It's that this Higgs field, which was always there, is interacting with particles in a way that we see as mass. It's like the Higgs field is setting the stage, and that's where the drama of particle physics plays out.
You got it. And the way the Higgs field interacts with different particles determines their masses. And that shapes the fundamental forces of nature and ultimately the structure of the universe.
This is really amazing stuff. So symmetry breaking, especially spontaneous symmetry breaking, isn't just some abstract mathematical idea. It's the reason why things are the way they are, why the universe is the way it is.
Exactly. And the crazy thing is that these ideas, which came from abstract mathematical considerations of symmetry, have led to some of the most important discoveries in modern physics. From predicting new particles to unifying fundamental forces, these symmetry principles have completely changed how we understand the universe.
So by studying symmetry, we're unlocking the universe's biggest secrets,
Yeah.
like a hidden code that controls how reality works.
That's a great way to think about it. And now we get to the really intriguing part.
Okay.
Because as we delve deeper into symmetry and symmetry breaking, we run into some profound philosophical questions.
Okay.
Questions that challenge how we understand objectivity, causality, and even the relationship between math and physics.
Okay, I'm ready to explore those philosophical depths. Hit me with those big questions.
So let's start with the relationship between symmetry and objectivity. As we've been talking about, symmetry principles are often connected to the idea that physical laws are objectively valid. But what does it actually mean for a law to be objective? Does symmetry automatically guarantee objectivity, or is there more to it?
Yeah, that's a question I've been thinking about this whole time. I can see how the fact that physical laws stay the same under certain transformations could be seen as a kind of objectivity. You know what I mean? It means those laws are true no matter the observer's perspective, like where they are in space, how they're moving.
Exactly. And this idea is really well expressed in a famous quote by Herman Weyl. He said, "Objectivity means invariance with respect to the group of automorphisms." Basically, he's saying that for something to be objective, it has to stay the same under the relevant transformations.
So if a law is symmetrical, it's like saying it's the same for everyone, everywhere, no matter how you look at it. That seems like a pretty solid basis for objectivity. But is that really all there is to it? Is symmetry enough on its own?
Well, it's a good place to start, but some philosophers argue that while symmetry might be necessary for objectivity, it might not be enough by itself. There could be other things that make something objective that go beyond symmetry.
Like what else could you need besides this idea of invariance?
Well, think about the fact that there are different levels of symmetry.
Okay,
You've got global symmetries where the transformations apply to the whole system in the same way.
right.
And then you've got local symmetries where the transformations can change from point to point. Does one type of symmetry mean something is more objective than the other? Like, is a globally symmetrical law somehow more objective than a locally symmetrical one?
Right, right.
These are the kinds of questions that philosophers are still trying to figure out.
It seems like the deeper we go, the more complex it gets. And what about the implications of symmetry breaking? Does breaking symmetry somehow bring in an element of subjectivity
Yeah.
to how we understand the universe?
That's another big question that really gets to the heart of things. If symmetry is tied to objectivity, does its absence mean there's some kind of inherent subjectivity? Or can we still understand objectivity even when those symmetries are broken? Especially with spontaneous symmetry breaking, where the underlying laws are still symmetrical, but the specific result isn't set in stone. It's like the universe is making a choice, breaking the symmetry in a way that seems almost random.
I see what you mean. It's like the universe has the potential for perfect symmetry, but then something happens that pushes it into a less symmetrical state. And that brings up all sorts of questions about things like causality, determinism, the role of chance in the universe. Does spontaneous symmetry breaking mean that there's a fundamental randomness at the core of reality? Or is there some deeper order, some hidden principle that we just haven't figured out yet?
Yeah, those are exactly the kinds of questions that physicists and philosophers are trying to answer. And we haven't even touched on what this means for the relationship between math and physics.
Oh, you're right. That's another huge part of this whole thing. If our most basic theories in physics are based on these abstract mathematical symmetries, does that tell us something about what reality really is? Is the universe fundamentally mathematical, like Galileo said? Or is math just a tool we use to describe the world? A convenient language, but not necessarily a reflection of some deeper truth?
And maybe even more fundamental than that, does the fact that these symmetries exist point towards a certain metaphysical view of the universe? Does it support a kind of Platonism, where these mathematical structures exist independently of the physical world as these eternal, unchanging forms?
Right.
Or can we understand these symmetries within a framework that's more grounded in experience, where math is seen as something that comes from human thought, a tool that we've created to make sense of the world around us?
Well, the more we explore symmetry, the more questions come up. It's like opening one door and finding a whole hallway of other doors, each leading to even bigger mysteries. It's exciting, but also a little overwhelming.
That's the beauty of it, right? This pursuit of understanding, the constant asking questions and trying to unravel the universe's mysteries. That's what keeps us going. And symmetry, with its simple elegance and its huge implications, gives us a really powerful way to look at those mysteries.
So where do we go from here? Are there any answers to these big philosophical questions, or are we just left to think about them forever, stuck in a constant state of wonder and not knowing for sure?
You hit the nail on the head. These are questions that have been debated for centuries, and they're still challenging and inspiring both physicists and philosophers. There are no easy answers. But that's what makes this exploration so rewarding. The search for understanding is a journey that never really ends, but the insights we gain along the way, that's what makes it all worthwhile.
I like that. Well, I think we'll leave our listeners to think about these mysteries for themselves. A huge thank you to you for being our guide on this incredible deep dive into symmetry and symmetry breaking.
It was my pleasure. It's always great to explore these topics and share the wonder of scientific and philosophical exploration with curious people.
And to our listeners, thank you for joining us on this adventure. We hope this deep dive has sparked your curiosity and maybe even inspired you to see the beauty and power of symmetry in the world around you. Keep questioning, keep exploring, keep wondering. Until next time.